Welcome back. So we were talking about constraint learning problems, and we basically discussed an intuitive approach that relies on incorporating the constraint directly into the objective. So we talked about basically the maximum displeasure function, which was defined through an indicator function that would lead to an equivalent problem, which is hard to solve. So instead of doing that, we approximated the maximum displeasure function by allowing softer displeasure, and that leads to sort of using linear or quadratic penalty functions. Okay, so we talked about the penalty-based method, and also we talked about the approaches based on the Lagrangian. So I'm going to spend some time here talking about the Lagrangian a little bit more, such that we can discuss the algorithmic solutions for constraint learning problems. Okay. So if you recall from the last slide, we had in the Lagrangian-based approach, we had a term like this that we were minimizing with respect to W, right? And we left open the question of how to find this Lagrangian variable or Lagrangian multiplier or the dual variable lambda. Okay. Now we're going to talk about this, but first let's call this function, which is a function of both W and lambda, the Lagrangian associated with the original constraint learning task. Okay. Now it is a function of two variables, W and lambda, right? And as we said, we are interested in minimizing this function with respect to W. Okay. Now let's see what happens when we minimize this function with respect to W. And note that the function is actually linear with respect to lambda. So in particular, it looks very simple with respect to lambda, but could look very complicated with respect to W. Now, what happens when we minimize the function with respect to W? We're going to get a function which we call the Lagrange dual function. So we are completely basically removing the impact of W by minimizing over W. So the resultant function will only be a function of lambda. Okay. Now, one claim is that this function is actually going to be a concave function, given that Lagrangian is linear with respect to lambda. And in particular, this is because if you have a bunch of functions that are, let's say, linear with respect to a variable, if you minimize over them, the result will be a concave function. And if you are maximizing, you're going to get a convex function. So let me try to demonstrate this by this simple figure. So imagine that I have, let's say, a bunch of let's say I have two convex functions, okay? And a linear function is also a convex function, okay? Now I ask you to find the maximum of these two functions, okay? So the maximum basically will be this. So it's going to be the second function that I drew until I hit this point. Then the first function lies above. So the maximum now is going to be this. So when you look at it, the maximum is going to be a convex function. Okay, so it is curving upward. On the other hand, so if I give you two concave functions, and then I ask you to minimize or find the minimum of the two, the minimum will be a concave function. Right, so this will be the minimum. Okay. So in this case, we have a linear function. So the linear function is in some sense both convex and concave. So let's say I have one linear here, I have another linear here, and I'm asking you to find the minimum of the two. Okay. So the minimum will be something like this, which is as you can see, a concave function. Okay. So these simple figures therefore kind of prove that when you have a bunch of linear functions and you're minimizing with respect to, let's say, W, the resulting function will be a concave function. Okay. So therefore, regardless of whether the original function is convex or concave or anything, and same for the constraint, by the virtue of minimizing with respect to w, the dual function is going to be a concave function of lambda. All right. So this minimization over w is also useful because the dual function is going to provide a lower bound on the optimal value of the original problem. Okay, and it's actually quite simple to see. For instance, consider any feasible point w tilde. So that basically means that it's a point at which h of w tilde is less than or equal to 0. Okay. Then we define the dual function to be the minimum of the Lagrangian over w. Okay. So this must be less than or equal to the Lagrangian evaluated at w star for any w. Okay. Because w star is w tilde is not necessarily the minimizer of the Lagrangian. All right. Now, what was the Lagrangian? The Lagrangian was the original loss plus lambda times the constraint. Okay. And given that w tilde is a feasible point, meaning that h of w is less than or equal to 0, I can basically drop the second term and basically only the first term remains, and that's the last value. Okay. Now this condition holds for basically what we established was that the dual function for any lambda is a lower bound on the last value of any feasible solution. Now the optimal solution by definition is a point that is feasible. It must satisfy the constraint and also achieve the lowest loss. Therefore, given that equation 13 here applies to any feasible solution w tilde, it must also apply to the optimal solution w star. Therefore, the Lagrangian, the Lagrange dual function provides a lower bound on the optimal value of our original objective problem, constraint layering problem. Okay. Now, given that we have this lower bound for any value of lambda, a natural question is what's the best lower bound? Okay. What's the tightest lower bound? Well, we have a lower bound for any value of lambda. So to get the tightest one, we want to maximize the lower bound over lambda. And this simple idea leads to what we call the Lagrange dual problem, where you basically want to maximize the Lagrange dual function, where the maximization is with respect to lambda. Okay. Note that here we're going to have a constraint on lambda, and the reason for that is that we basically needed lambda to be larger or equal to 0 to make sure that we have to make sure that, we can find points that satisfy the constraint h of w less than or equal to 0. In particular, lambda has to be non-negative to make sure that this constraint is satisfied. Okay. All right. So what's the Lagrange dual problem? Therefore, we are maximizing with respect to lambda, and note that the dual function itself had a minimization with respect to w in its definition. So therefore, our overall Lagrange dual problem is as follows: maximize with respect to lambda, minimize with respect to w of basically the original loss plus lambda times the constraint. Okay. All right. So how is this related to the original problem? So we just mentioned that the Lagrange dual function is a lower bound on the optimal value. So for any lambda is a lower bound. When I maximize over lambda, I still get a lower bound. So that means that if I solve this problem and find some solution, the solution is going to lead the value of the solution will be less than or equal to the value of the optimal solution for the original problem. Okay, and this is sometimes called weak duality in the optimization literature. Now we can actually show equivalence between the two, so such that the dual value is equal to the original value under certain assumptions. For instance, if and these assumptions are sort of not too important for us, so I'm just mentioning here for your interest. Under certain assumptions such as the Slater condition, the strong duality is satisfied, and in particular, what that means is that not only we have a lower bound, but that lower bound is tight, meaning that the value of the dual problem is exactly equal to the value of the original problem. Equivalently, sometimes this can be represented as follows. Equivalently, we can say that when a strong duality holds, we can change the order of the minimum and maximum, and nothing changes. So we get an equivalent problem. So we have the dual problem here, where we are maximizing with respect to lambda and minimizing with respect to W. You can change the order of the minimization and maximization to get this problem. Okay. And this problem can be shown to be equivalent to our original problem, where we were minimizing. So the three will be equivalent to each other, where we were minimizing the original loss such that h of W less than or equal to 0. Okay. So the second problem is equal to the original one, and under a Slater condition, a strong duality holds, and the first problem is equal to the second one, meaning that we can change the order of the minimum and maximum, and nothing changes. Or in other words, through the dual function, not only we get a lower bound on the optimal value of the original problem, but we actually get a tight lower bound. All right. So the reason I mentioned this is that basically, now that we have this problem and we see this connection between the original problem and the min-max problem or the maximum problem, we can try to apply iterative algorithms to calculate not only W, but also the precise lambda we need to make sure that our constraints are satisfied. Okay, so to a reasonable accuracy. So therefore, one implication is that we don't need to, for instance, apply hyperparameter optimization or approaches like that, or heuristics like that, to determine a good regularization parameter. Thanks to this elegant theory of duality, we can calculate what's the best sort of regularization parameter, or the Lagrange multiplier in this case, to ensure that we can find a solution that is optimal and also crucially feasible, a solution that satisfies our hard constraint as part of the constraint learning problem. All right. So therefore, this leads to a host of different iterative algorithms where, as I mentioned, they try to solve this max-min or min-max problem iteratively. Okay. So here is one way to talk about almost all of them in a very simple and abstract way. Let L to be the Lagrangian function we talked about, or it could be the augmented Lagrangian function, where in addition to the linear term, we could also, let's say, include the quadratic term. Okay, and that has some benefits in terms of numerical stability and also the speed of convergence of our iterative methods. Nonetheless, let L to be the Lagrangian function, and note that what we were interested was to minimize with respect to W, maximize with respect to lambda of this Lagrangian. Okay, and we can do so iteratively. So in particular, for t iterations, let's say we have some solution Wt and lambda t, we minimize the Lagrangian and then find the next solution. Okay, so joint minimization with respect to both W and lambda could be could be challenging in a lot of scenarios. Therefore, and could be infeasible to do actually in general. Therefore, what we typically end up doing is what we refer to as alternating optimization. So that means that I'm going to first, let's say, keep lambda fixed and optimize W, and then I'm going to keep W fixed and then optimize lambda. In particular, we can have this simple iterative procedure where we minimize the Lagrangian with respect to W when we set the lambda, the Lagrange multiplier, to be lambda t, our current solution. Once we determine W, the next solution, Wt plus 1, we're going to now fix W and maximize with respect to lambda. And we're going to continue this iterative procedure such that the method converges, or we find a reasonably accurate solution. Okay. Now we can actually relate this procedure to the ideas we've talked about in class so far, crucially gradient-based methods. In particular, after some approximations, for instance, writing the second order or the first order approximation of the Lagrangian around the current solution, and under certain assumptions, we can actually interpret these kind of algorithms or this family of algorithms as gradient descent or algorithms that are trying to apply gradient descent with respect to W, because we are minimizing with respect to W, and algorithms that are applying gradient ascent on lambda because we are maximizing with respect to lambda. In particular, we can think of these methods as applying this procedure. In each iteration that you have, let's say, a solution lambda t, the current Lagrange multiplier, and let's say Wt, the current model parameters. You take the gradient of the Lagrangian with respect to W and use that as your update vector to update the current parameter and move from Wt to the next parameter, Wt plus 1, according to some learning rate eta. Okay. Once we find Wt, or the Wt plus 1 rather, we basically apply gradient ascent on lambda now. So that means that I'm going to go from the current lambda to the next one by following the direction of gradient times some learning rate, where the gradient is with respect to lambda, not W, and also we are using the positive sign here, not the negative sign. And again, the reason for that is that we are maximizing with respect to lambda, not minimizing. Okay. And finally, we kind of need some sort of projection to make sure that the value of the lambda that we are finding is feasible. Okay. And the reason for this projection, to make sure that lambda is positive. So again, remember that this notation was return the maximum of 0 and the input. So it means that the output is always non-negative. And the reason we apply this projection, so it's kind of a projection on the positive orthan, is that we have this constraint that lambda has to be non-negative. Okay. So therefore, the overall method is like applying gradient descent without any projection on W, while it applies projected gradient ascent on lambda to update the parameter as well as the Lagrange multiplier. Now, this is basically, again, like an extended version of gradient descent that we talked about earlier in the class. Naturally, we can talk about stochastic algorithms. We can talk about utilizing a stochastic gradient and SGD to perhaps have a more efficient method for large-scale learning problems. We can talk about approaches that incorporate momentum or adaptivity or variance reduction to accelerate this procedure. Okay. Now, and I would say that these are very interesting problems, and to some extent, some are answered and explored. But when it comes to highly non-convex functions that we observe and have to deal with in the context of optimization for deep learning, many of these questions remain to be answered. All right. So that what we talked about was basically approaches based on based on the Lagrangian formulation or the augmented Lagrangian formulation that require updating two parameters. We have to update our original model parameter W, which is sometimes called the primal variable, but we also have to update lambda, which is sometimes called the dual variable. Okay. There is actually a very elegant idea that goes back to Boris Polyak in the 1960s that kind of relies on updating only the original model parameter, and it doesn't do anything with the dual variable or the Lagrange multiplier. Okay, so and the reason I'm mentioning this is that this algorithm, despite being very simple, is quite effective, and in a number of settings, it can actually be shown to be an optimal algorithm. And recently, it has seen a renewed interest, especially in the context of larger scale optimization and for deep learning. Okay, so to see this algorithm and discuss its motivation, let's consider our original problem, where we want to minimize, let's say, some loss function f of w, and for us, typically f of w again is the average loss over the entire training data, subject to some constraint, such that h of w is less than or equal to 0. Okay, and assume that we are working with an iterative method, or we want to basically have iterative algorithms. For instance, let's assume that we have some current solution wt. Okay, now intuitively, if wt is a feasible solution, constraint becomes irrelevant. Okay, so if I'm currently feasible, I don't need to even care about the constraint at this point. Okay, so this is one way to demonstrate this idea. Let's imagine that you have, let's say, some constraint that you want to maximize or minimize, and then this is the range of all feasible values. So anything beyond is infeasible. So we are not interested in that. Okay. Now let's say that I have a current solution here. Now if I want to minimize it, let's say using gradient descent, does it really matter what my constraint is? No, I can just apply gradient descent and move here. Again, if I have a feasible problem, a feasible point, it doesn't matter to incorporate the constraint as part of my iterative algorithm. I can just continue applying the gradient descent with respect to only the objective to update my variable. So therefore, we don't need to intuitively, constraint need not be considered for an iterative wt as long as our solution is sufficiently feasible. Okay, so by sufficiently feasible, I mean that h of wt is less than some predefined threshold epsilon. Okay, and if that's the case, what we can do, we can just, as I mentioned here, apply gradient descent or similar methods to update a parameter. For instance, I can move from the current solution to the next one by following the negative direction of the gradient of the objective, only the objective, and don't consider the constraint at all. Okay. So this is for the case where we have access to a feasible solution. On the other hand, if I have access to a solution that is not feasible, such that h of wt is beyond my predefined threshold of infeasibility epsilon, we may want to prioritize the constraint over the objective. Okay. Okay. How should we prioritize the constraint over the objective? Well, we are looking for values or models that for them h of w is less than or equal to, let's say, 0. In this case, h of w is larger. So we have to find a w that kind of lowers the value of h. Okay, so we have to lower the value of h, minimize h, and a natural idea to do that is by applying gradient descent. Okay, so we can prioritize the constraint when we have a solution that is not feasible or is not sufficiently feasible by again applying gradient descent, but this time instead of using the gradient of the objective, we're going to use the gradient of the constraint. Okay? So that means that I'm going to go from the current solution to the next one by following the direction of the negative of the gradient of h, my constraint. And given that this is gradient descent, intuitively, I'm going to find a solution that has a lower h value. Therefore, it is more likely to be feasible. Okay. So therefore, the idea is that depending on amount of violation, we're going to switch the gradient in gradient descent. So therefore, we apply the following procedure for capital T number of iterations. If the constraint is sufficiently satisfied, we perform our usual gradient descent. On the other hand, if the constraint is not sufficiently satisfied, we apply gradient descent by switching the gradient from gradient of f to the gradient of the constraint h. Excuse me. Right. So therefore, one sort of conceptual difference between this method and what we talked about in the previous slide is that here we are handling the objective and constraint at different times. So in each iteration, I'm only going to handle my objective or my constraint depending on whether the current solution is sufficiently feasible or not. Whereas in approaches based on the formulation of Lagrangian, we are handling both of them simultaneously. In each iteration, not only we update W, but also lambda to make sure that we are simultaneously progressing toward minimizing the value of the objective while ensuring that our solutions become feasible. Okay. So we kind of might expect some connection between the two, and we could actually make a connection between the switching gradient method, or SGM, and the Lagrangian formulation. Okay. So in particular, we can think of SGM as a kind of a stochastic gradient descent for the dual problem. Okay. So let's consider this optimization problem, which again is equivalent to our original constraint learning problem. We want to minimize with respect to W, maximize with respect to lambda of f of W plus lambda times HW. Okay, and let's say that somehow I was able to solve the inner maximization problem for any value of W, and I find lambda star. Okay, so let's say lambda star, which is non-negative, is the maximizer of the inner maximization problem. Okay, so generally this will be a function of W, but for simplicity of our intuitive discussion, let's just assume that it's a constant. It does not change with W. Okay. Then what will happen is that I basically need to solve this problem. Okay. So my problem reduces to minimize only with respect to W of f of W plus lambda star times h of W. Okay. Note that lambda star is non-negative. And here I'm assuming that it's constant. It does not depend on W. So what I can do, I can divide basically my my objective with a constant and still get an equivalent problem. So in particular, let's divide the objective by 1 plus lambda star. So therefore, we're going to get this equivalent problem. Okay. Now this is an objective function, right? So the problem is unconstrained, and then we can apply our favorite algorithm, let's say gradient descent. And if we do that, we're going to have this update. We're going to go from the current solution to the next one by following the direction of the negative direction of the gradient, okay, with some learning rate. What's the gradient? Well, I'm assuming that lambda star is a constant, okay. So the gradient of this objective is nothing but what I've written here. Okay. Now let's make this observation. Okay. So here I kind of have a weighted average of the gradient of the objective and the gradient of the constraint. Okay, and the weights are non-negative, because 1 is non-negative, lambda star is also non-negative, and they also sum to 1. If I add 1 over 1 plus lambda star and lambda star divided by 1 plus lambda star, I'll get 1. So therefore, I can think of this as an expectation. So what I have here, therefore, can be thought of as being the gradient of a stochastic function, okay, where the stochasticity is due to some random variable z that takes only 2 values with probability 1 over 1 plus lambda star and lambda star divided by 1 plus lambda star. So this basically implies that the stochastic gradient algorithm for this method is that you sample one of these gradients with the corresponding probability. So if the first choice is chosen, which is chosen with probability 1 minus 1 over 1 plus lambda star, I'm going to calculate the gradient of the objective function. In the other case, which is chosen with probability lambda star divided by 1 plus lambda star, I'm going to gain access to the gradient of the constraint. Okay. So clearly here you see the connection between the stochastic between switching gradient method and optimizing the Lagrangian formulation. Okay. So in SGM, as we talked about, depending on how much we are in the violation of the constraint, we're going to use either the gradient of the original objective f or the gradient of the constraint. Okay. And if we are infeasible, we use the gradient of the constraint. If we are feasible, we use the gradient of the objective. We can associate these two cases with the value of lambda star. When lambda star is near 0, that kind of means that we have a solution that is feasible. Okay. So therefore, what this means is that in terms of selection of these two gradients, it's more likely for me to select the gradient of the objective. So I very rarely select the gradient of the constraint, and I don't need to, because the solution I have is sufficiently feasible. On the other hand, when lambda star is basically large, let's say approaches infinity or some large number, that means that the chance of selecting the gradient of the original objective f is very, very low. And it kind of makes sense, because in the second case, I'm in the violation of the constraint, so I have to prioritize basically feasibility over optimality. So that basically concludes like a very brief overview of some computational approaches that we can use for constraint learning problems, where in addition to the original training loss, we may want to care about some additional constraints that arise from certain contexts. For instance, as we talked about, robustness, fairness, or minimizing the memorization tendency of our deep learning models. Now, one thing we didn't talk about too much in this lecture was about, again, like the convergence of these methods. For some of these, I would say that's beyond the scope of the class, and I refer you to standard courses on convex optimization. The switching gradient method, however, something that you can actually analyze in very, very simple cases without any difficulty. So the analysis that we talked about for the gradient descent algorithm without any constraint can be extended with minor difficulty, I would say, to study the performance of the switching gradient method. Okay, that's why I would say the switching gradient method is an appealing method, especially when it comes to solving constraint learning problem at a very large scale. All right, so this brings us to the end of our module on contextually constrained deep learning. And in the next module, we're going to talk about some special topics that range from, let's say, the overparameterization, talking about higher quality solutions, and also talking about generative models. I'll see you in that module.